Hi everybody, today I'll show you how to do problem number 9 from chapter 8. Number 9 states, a light rigid rod is 77 centimeters long. Its top end is pivoted on a low friction horizontal axle. The rod hangs straight down at rest with a small massive ball attached to its bottom end. You strike the ball, suddenly giving it a horizontal velocity so that it swings around in a full circle. What minimum speed at the bottom is required to make the ball go over the top of the circle? Okay, so here I've drawn my diagram. Here's the ball at the bottom. We are told it's being hit. I'm going to assume it's in this direction. It's going to swing around in a full circle. And defining this way is the positive y direction, that way is positive x direction. And the only information they really give us is the length of this bar attached to it is 77 centimeters. So what we are trying to find is the minimum speed that will get the ball entirely around the circle. So that means is you want to find the minimum speed at which it can even get up to its highest point up there. So what we're going to say is at the top, we're going to use this equation. So the mechanical energy is equal to the kinetic energy plus the potential energy. At the top, assuming we hit at the minimum speed, it will actually slow down as it goes up and will essentially reach zero kinetic energy. So what we're going to do is plug in 0 for k, and then we can substitute mgy in for potential energy. Then we know y if we define this point as 0 at its lowest point. We know that y is the entire diameter of the circle upwards. If the radius is 77 centimeters, then that means that the y value would be 2 times the radius. So we can start plugging that in now. The mass we don't know. We'll just call it m for now. G is 9.8 meters per second squared. And the y value is the height, which is 0.77 meters plus 0.77 meters, which is that plus that. Now we plug that all into a calculator. We would get 15.092 m. Okay, this m right here means mass, not meters. Our units is going to be joules, since meters times meters second squared, and this is going to be assumed to be kilograms. Now that we found the total energy of the system, we can use the same equation to evaluate it at the bottom. This time, however, we're trying to find the kinetic energy, which we can find by the amount of energy we use to hit the ball with at the beginning. So, also at the bottom, the potential energy, as we know, is equal to mgy. And since we said that at the bottom y is equal to 0, therefore the potential energy at the bottom must be equal to 0. And since in this whole problem energy is conserved, the energy we found at the top is the same energy of the system at the bottom, which is 15.092 mass, not meters, times joules, or not times joules. Joules is the unit. Alright, now we can substitute this in for k. And we can see that we can cancel or divide out m on both sides. M, if we say that was kilograms, we can also change this unit, since we divided by m on both sides. Joules becomes meters squared per second squared. Multiply 2 on both sides, and we get 30.184. So basically, what I just did is multiply 2 on both sides and divide by m on both sides. Now, if we take the square root of both sides, we would get 5.49 meters per second, and that would be our final answer.